All right. So probably hold off a little bit on talking about the exam until Friday, just because I haven't gotten to go through and grade all the short answer portions yet. So there's still like 20 points missing. But I think overall they didn't look too bad, kind of factoring that in. If you have individual, so I think there's a couple questions on number 7. So there was an answer that was duplicated, but it was wrong. So it didn't matter. If you selected either one, it was the wrong answer anyways. If you have any other questions, if you're kind of going through the exam, I'll put up, you now should be able to see all the correct, after today's class, see the correct answers. So if you have any questions about how to work through any of them or specific questions on a certain problem, feel free to kind of reach out and I can try to help explain it to you or kind of meet with you to go over it. Other than that, I will post kind of an online quiz today that you just have to get on and do it. Basically going to ask you that Monday before Thanksgiving, which should be our last kind of like in-person class. Since there's not a whole lot of you kind of show up in person, probably more relevant to you guys. But also even if you kind of sign in and watch it on Zoom. So basically I just ask your preference on there. If you want to have kind of the standard like we are right now and have a kind of meet in person, we'll do a Zoom call and then I'll post the video afterwards. Or if you just kind of want to do a Zoom call and I'll post the video afterwards, or kind of the third option is none of us meet synchronously. I don't use Zoom, but I still record a lecture that you can watch. So kind of which of those is kind of your preference for that Monday of Thanksgiving week. I know I kind of, not just this semester, but in general, people are usually pretty antsy to get out of here, travel plans. So, that'll be posted up there. Select the option that kind of you prefer. And I'll just kind of look at the results and I'll have a kind of plan for that kind of next Monday, kind of mention what we're going to do for that day. Okay. Like I said, I'll talk more about the exam on Friday once I have them all graded, which I should be getting them done at some point tomorrow, right? I'm going to start them tonight, but my guess is I won't have them all done until tomorrow, okay? Any other questions for me before we get going here? Also, I did post a Connect assignment. We clearly haven't covered anything that you can start working on it. But as we continue, we move through material, you should be able to kind of start chipping away at that, okay? All right, that should be all the housekeeping stuff, I think. So, prior to the exam, we're doing a lot of confidence intervals hypothesis testing. We're going to kind of stay in that same lane for a bit. But hopefully, I'll show you kind of what we're going to do with 2 populations. Allows us to make some more interesting statements, right? Gives us a little bit more power. So I'll double check that I'm recording. Yep. So we're going to have very similar scenarios as we did before, right? We can build confidence intervals for 3 different types of scenarios. It's just now we have 2 populations we're sampling from. We know the population variances is kind of the first scenario, or we're looking at proportions. Same as before, if we know the population variance or we're looking at proportions, we're using the standard normal distribution. So nothing's really changed there other than we have 2 populations. And if we don't know the population variance, all we have is sample variances, we're using the student t. So nothing's different, right, in terms of kind of the principles behind it. It's just now we have 2 populations. We're looking for the difference between those 2 populations. And I'll give you some examples here in a second. And then we can also do the same thing for hypothesis testing, same 3 sort of scenarios. And then our types of tests also don't change at all. We still have a left, a right, and a 2-tailed test. So the only thing that's going to kind of be new in this next batch of stuff we do is this thing called matched pairs, right? So matched pairs is a little bit different. We'll talk about that when we get to it. But really these confidence intervals and hypothesis tests for the other 3 scenarios are going to look really similar to what we did with 1 population, just a couple more moving parts, okay? Excuse me, so like the motivating examples that we'll be using are, what's the difference between econ and theater majors starting salaries? We have some known population variances. Could I build a confidence interval? Right? I might then have, okay, I have 2 different time periods, 2011, 2010. I have the proportion of people who were in favor of the Affordable Health Care Act in both those years. What's a confidence interval for that example? I then have response times, the average response times of people who are texting and not texting while driving. What's kind of the difference in response times, right? Can I build a 90% confidence interval for that? Right? But here I only have sample variances here, yeah. So those are my kind of three motivating examples. The one that we'll really focus on today is the one where we know our population variances. So we had two populations that we're sampling from, and kind of our motivating example was, what's the true difference between econ and theater majors starting salaries? So my first population I sample from, maybe this is my econ majors, I'm going to have some sample size for that group and calculate a sample mean. We then are dealing with scenarios where we assume that we know the population mean for kind of econ major starting salaries, and there would exist some, population mean. Whether or not I can observe it, once we get to confidence intervals, the whole reason we're doing that is because we actually can't observe the true population means from these two groups or two populations. Then for group two, right, you can do all the same things. They'll have their own population variance, population mean, sample size, and sample mean, right? What ends up being true, and I'll kind of walk through this a little bit more on the board here, is the difference between those two sample means, so x1 bar minus x2 bar, the difference in those sample means that you find, the difference between econ and theater majors starting salaries, will be normally distributed, right? And it will be centered around whatever the true population difference is. Right? I then kind of see my standard deviation will be, I'll talk through this in a second. I'll come back to these equations because I think it makes a little more sense if I walk through it. So before, what we were doing was, with one population, the distribution of our sample means was normally distributed around whatever our population mean was. We then said the variance for my sample means was the original variance of the data I sampled from divided by my sample size. Okay? With two populations, what we're saying is, well, now the statistic I'm interested in is the difference in these two groups' sample means. So econ and then theater major starting salaries. For now, in a second, I'll show you why this is, but for now, I'll kind of just walk through and take it as gospel, I guess. So what ends up being true is for that new statistic that we're interested in, not just a sample mean, but the difference in these two group sample means, it'll be normally distributed around whatever the true population difference is. So the population mean of each group, whatever that true difference is, our sample differences will be centered around that. Now, we usually can't observe this, right? But that we do know that that'll hold to be true. Now, the variance for this new statistic that we're interested in, which is now the difference in sample means, it's simply going to be take the variance from the first group's sample means and add it to the group's second group's variance for its sample means. Well, we know the equation for the variance of a sample mean is this. So now it's just going to be add that up from group one to group two's variance, right? So each group's population variance divided by its sample size, which both of these just represent the standard deviation, the variance for the first group sample mean, add that to the variance for that second group sample mean, okay? So if I know that's going to be true, right, if I just accept that as true for now, I need a so if we assume that that's true, then we can think about something else, right? So before, when we wanted to calculate a test statistic, or actually, no, sorry, I jumped ahead. Before, when we wanted to do a confidence interval, this was the equation that we were using, where this guy here represented the standard deviation of my sample means, right? So we were looking at the statistic we were interested in, going a certain number of standard deviations away to get our lower and upper bound, such that alpha over 2 would kind of be on either side of the confidence interval. And if this is the number of standard deviations we want to go away, well, we have to multiply that by the standard deviation value, right? If I want to go 2 standard deviations away, I have to take 2 and multiply it by the standard deviation of the statistic I'm interested in. Well, now you can think about it as the statistic you're interested in, right, is the difference in those sample means. Well, you know the population variances, so you still get to keep using that standard normal Z table. And now you'll multiply by the standard deviation of the statistic that you're interested in. Well, the statistic I'm interested in is the difference in my sample means. Well, I know the variance is going to be equal to just the variance of each sample mean added up. So the standard deviation would just be the square root of all this, right? So the square root of each group's population variance divided by its sample size. So it's the same kind of setup. It's just we have a couple more moving parts. We have a couple more things we'll have to plug into these equations now. But we still look up this z-score the same way, right? And so that'll end up being our confidence interval equation, okay? Any questions on anything so far? Let's see here. Okay. So I want to give you a little bit of more intuition that's behind why this is true. Why are my sample mean differences centered around that true population difference? So I think this is a good way to look at it. So let's say, well, I can get rid of this actually too. So let's say, I don't know, we've got group one, so maybe this is our econ major starting salaries. It would be centered around whatever the true population mean is. We then have kind of group two, which is our theater major starting salaries, and they kind of have their own distribution when we're looking at the sample means that we could see from those two groups. Right? So if I wanted to then kind of draw out a graph for what the for what the sample difference I'm going to find between these two groups, I could think about it like this. So now I want to know the distribution between the sample mean I see for econ majors and the sample mean from theater majors, right? Well, if I look at this, what's going to be the most likely outcome I see for this sample mean difference? Well, the most likely outcome I see for the sample mean for econ majors, remember this y-axis is kind of telling you the probability of seeing these different values. The values near the mean are more likely for me to see than the values farther away. So the most likely value that I'll see is right here, right, the highest point of the distribution. What's the most likely outcome I see for the sample mean for theater majors? Highest point of the distribution. So the most likely difference I'll see would be whatever that value is that I subtract the true population mean from the true, for econ majors, from the true population mean for theater majors. So if I'm thinking about what's the most likely outcome for me to see, it's going to be whatever that difference is between the true population means. Then what's the next most likely outcome for me to see? Well, something here minus something from here, or something here minus something from here. So it's a little bit less likely, right? And I can kind of keep thinking, okay, what are the next most likely differences I see, right? And I would just get this kind of nice normal distribution, right? But the reason kind of why it's centered around that true population mean, you can kind of think about it as, well, those population means are like the most likely outcome I would see for my sample mean. Okay, like I said, that's just trying to give a little bit of intuition as to why that holds, right? There's a mathematical proof we could walk through, but I think just the visual there kind of gives us a pretty good intuitive idea, right? So we had that equation for the confidence interval where we said this is kind of like our sample mean before. Now we just have a difference, and here this is like, you know, basically the standard deviation of the statistic that we're interested in. So things change a little bit, but pretty similar, right? So I'll walk through an example, right? Before I do that, here's kind of our steps, right? We have to identify the pieces of information we need. We need a sample mean, a population variance, and a sample size from each group. Right? We also have to identify alpha, right? What confidence interval do we want to build? I use alpha divided by 2, so I have alpha over 2 on each side of my confidence interval to find that z value. And then it's just a matter of plugging and chugging, right? Now we've got everything we need, just plug it into our lower and upper bound equation, okay? So if we walk through an example, back to that econ theater majors, right? Let's say we've got 40, or our first group is these econ majors, so 40 is our sample size for that group, 45,000 is our sample mean, and we somehow have this known population variance of 9,000. I then look at my second group, which is theater majors. They have an average starting salary of 33,000, so their sample mean is 33,000, and a population variance of 6,000. What would the 95% confidence interval be for the difference between econ and theater majors starting salaries? Well, right, I identified the piece of information I needed. Right? I had group one's average salary, group two's, both groups population variances, both groups sample sizes. And at the 95% level, right, my alpha is going to be 0.05, right? Whatever's outside my interval, but in decimal form. So I need to look up my z-value. Two ways we could do this. We can, oh, I thought I had them open, but apparently not. We could use that z table, right? Because we know that's the distribution we should be using. But there was kind of a shortcut that we could also use if we use the student t table. So show you first in the standard normal table. We wanted an alpha of 0.05. So 0.025 on either side, alpha divided by 2 on either side. We go here, what value is closest? Ooh, this is exactly in there. So negative 1.96, right? So 0.025, negative 1.96. Now remember, kind of that negative and positive sign are already built into our lower and upper bound equations. So we wanted, negative 1.9, negative 1.96 standard deviations below the sample difference we found at the lower bound, but positive 1.96 standard deviations above that sample difference we found at our upper bound. Okay. Once I have that, it's really just plugging everything into those equations and kind of making sure we can get this into our calculator okay. All right. Now, one thing to kind of think about what we're doing here, when we look at that sample difference we found, we're going to be building our confidence interval around that difference. So here, the sample difference was 12,000. We were then going to build and get our lower and upper bounds, so that 12,000 would have been exactly in the middle of our confidence interval. Okay. But what's kind of interesting here, so I've got about 11,950, 12,000, something just above 12,000. So I'll use these numbers to kind of help us think about why looking at confidence intervals for two populations starts to we can make a lot more interesting statements, right? So it was what, somewhere like 12,500 and 11,000. We'll just say that's what it was, right? To give us some easier numbers. So with 95% certainty, right? When I'm thinking about, I'm trying to figure out where the true difference between econ and theater major starting salaries, trying to figure out where that true difference is. So with 95% certainty, I can say it's somewhere in between these two values. Well, notice all of these values are positive. So what I'm saying is with 95% certainty, this true difference is going to be positive values, right? Or somewhere between 11,500 and 12,500. So what I'm really saying, if I rearrange this equation a little bit, is that with 95% certainty, econ majors are making more than theater majors. Not only can I say they're making more, I can say they're making somewhere between $11,500 and $12,500 more, right? Excuse me. Now, what would happen if instead my lower bound was, I don't know, negative 2,500? Well, it could be that I have positive values for this difference, but it could also be that I have some negative values for the true population difference. Well, if this was negative, now I'm thinking about, well, that actually would mean that the econ majors are making less. It could be 0 in this range, which would mean maybe one of the true population differences could be 0, or that they're making the same amount. Right? So anytime I have a confidence interval that kind of overlaps that 0, I can't really make as interesting of statements. But here, ours originally was just all positive values, pretty high values too, in a pretty narrow range. So we could say with 95% confidence, econ majors are making about, somewhere between these two values more, right? Between 11,950 and 12,036. Any questions on this one? Good. Okay. So what if we wanted to do a confidence interval, another example, kind of go through a little bit quicker maybe. But I've got, maybe I think Indiana is safer than Ohio. I look at crime rates for 24 years in Indiana and 24 years in Ohio, right? So my sample size for each group here is going to be 24. I have 24 years of data for each state. I find the mean robbery rate, sample mean, is 109 in Indiana and 163, per 100,000 people in Ohio. I somehow have the population variances. Like I've said before, it's unlikely in a scenario like this that I would have the population variances, but we're first going to see how we do this when we know them, then transition later on to what happens if we only had sample variances. So we've got everything we need. So if I think about when I set this confidence interval equation up, now what I'm looking at is kind of the difference between Indiana and Ohio. And I want to know where that true difference is. Well, the sample difference I found was what? 109 minus, I think it was 163. So what, negative 54? So my confidence interval is going to be centered around that value of negative 54. Now, if I look at the answers I have there, hopefully I can figure out D can't be the answer at all, right? Because my sample statistic, right, what I'm building my confidence interval around, negative 54, isn't even in that interval, right? I think every other one, looks like it's kind of smack dab in the middle, so we really can't rule any of the other answers out, okay? All right, so at this point, we've got everything we need other than that Z value. So how do I find the Z value? Well, what's my alpha here? 95% confidence interval, so alpha is 0.05. I need alpha over 2 on either side, right? But I don't even have to go to the table now because why? What confidence interval did we find before? Oops. The 95%. Alpha over 2 is going to be the same value. When I look it up in the table, I'm going to get that same Z value of 1.96, right? So, for these examples, you'll start seeing the same kind of Z values using confidence intervals pop up a lot because we always want the same three levels of alpha, 0.1, 0.05, and 0.01. So we're always going to be kind of finding those same Z values. Now, one thing I forgot to do, I had said it and then I left. I said there was two ways to find it, right? So if I didn't use the Z table to find that Z value that I wanted, to give me alpha over 2 on either side, I can use the student T table, right? I know I wanted 0.025 on either side of my confidence interval and just go all the way down to the very last row, which represents a student T distribution with degrees of freedom of infinity, which would actually be the standard normal distribution. So if I did that, I'd still get that same 1.96, right? So there's two ways we could do that. And then from that point, it's really just plugging everything into our equations, right? We've got that Z value now of 1.96. Plug in those sample means. We know that we're going to be centered around that negative 54. And we end up getting kind of our lower and upper bound there, okay? So here, what can I say with 95% certainty? If my confidence interval is only values in between negative 54 and negative 43 and negative 64, with 95% certainty, I could say that Indiana has all right, so I'm thinking about, I was trying to find what this was, right? If I only have negative values for what that true difference could be in my confidence interval, right? I only had negative values. So I know that difference is less than 0, right? So what would that mean if I rearrange this equation a little bit? The only way this is less than 0 is if Indiana has a mean that's less than Ohio's, right? That's the only way I get a value here that's less than 0. So with 95% certainty, I can say that the true difference between Indiana and Ohio crime rates is something less than 0. Indiana's is lower, right? In fact, I can go a step further. I can say Indiana's is somewhere between 46 and 64 fewer crimes, right? Because I know the difference has to be somewhere in between negative 64 and negative 46, right? So it starts to, with these two population examples, we can really start to compare groups and make some pretty powerful statements. So maybe Ohio needs to get it together. I like to pick on Ohio. That's what happens when you grow up in Michigan, I guess. So we can do confidence intervals, right? We can also do hypothesis testing with two populations, right? So let's say we want to test for whether or not, what the difference between two population means is. What we're going to call this difference in the way that we write this in our hypothesis is capital D. So capital D just represents the mean from group 1 minus the mean from group 2, okay? So we're going to assume that difference is some value. We'll call that D subscript 0, okay? Almost all the time, we're going to use, I shouldn't say almost all the time. I will show you a couple examples once we get to doing this in Excel, what happens if this isn't 0, and I'll maybe talk about it a little bit. But in terms of the problems I have you work through on the exam or on homeworks, we're always going to assume that this difference is equal to 0, okay? So we would still have, in theory, right, we would have a right, a left, and a two-tailed test where we're saying, is that true difference greater than some assumed true difference, which I said we'll be using 0? Is that assumed true difference is the difference less than some assumed true difference, which I said we'll be using 0? And is it not equal to? All right, so same two-tailed and one-tailed test we had before. We still use the alternative hypothesis to identify what type of test we have. It's really exactly what we were doing before, just with an assumed true difference and an actual difference instead of an actual population mean and assumed true population mean, okay? So our steps look no different. They're the exact same. The only thing that's going to change, right? So our p-values, everything's going to be the same. We find our p-values the same way. Multiply by 2 for a two-tailed test. This is nothing new. These are actually just repeated slides because the process literally doesn't change from what we were doing with one population. We would find the same critical values for the different types of tests and the different alphas. The only thing that changes is the test statistic that we'll have to use. So where does this kind of come from? And I want to kind of show you something about the assumed true or the null alternative hypothesis. So before, we were finding the test statistic with this equation, right? We were taking the statistic we're interested in, subtracting the assumed true mean, and dividing by the standard deviation of that statistic we're interested in, right? This gave us our Z statistic, right? Our test statistic. Well, now our Z statistic, we're no longer interested in the sample mean, but the difference in our sample means. You could almost think about this as kind of our sample difference that we found, the difference between those sample means. We would then not, subtract the assumed true population mean, but we would subtract the assumed true population difference. We then divide by the standard deviation of the statistic we're interested in, which is the difference in sample means. So it's the same sort of setup as what we were doing before. It's just now the statistic we're interested in is kind of like, combining two, looking at the difference between two statistics. And the standard deviation will be a slightly longer kind of equation because we said to get the standard deviation for the difference in sample means, we had to take the variance of each sample mean and add them together. And then if we want the standard deviation, take the square root of it all. Okay? Now, if this is usually 0, that's kind of nice, right? Because subtracting 0 doesn't do anything, so I can essentially ignore it. So that's why on the slide, you could basically just drop this second part off, right? It's always going to be 0 for us. Okay. So why do am I just like lazy and I don't want to teach you about how do we do this if we have different assumed true values? Well, no, the reason why we often use 0 and why I'm okay just showing you examples where it is 0 is because those are really the most interesting. I mean, that's really questions that we would quite often have about differences between two groups. If we think about it this way, if I said, right, let's assume that I want to find that this difference is greater than 0, right? That's my alternative hypothesis. What would that really be saying? Remember, this represents kind of the difference between group 1 and group 2. So what I'm really saying is this, which if I rearrange this, what I'm really saying is, does group 1 have a greater mean than group 2, right? And then what if I say, if I assume that true difference is 0 and I say, is it less than 0? Well, now what I'm saying is, does group 1 have a smaller population mean than group 2? What if I'm saying, is it not equal to? Well, now I'm saying, does group 1 and group 2 just have different means, right? Are their means just not the same, right? So those are kind of three just typical tests you would want to, when you're comparing groups. Is one greater than the other? Is one lower than the other? Or are they anything different from each other? Right? So that's why we can use that value of 0 as the assumed true difference. And really that covers a lot of the types of examples we'd want to do two population hypothesis testing with. Right? Okay, so kind of the example that I want to work through here is, let's say we've got two population means where we kind of know the variances. So I've got two different time periods, an older time period and a newer time period. And I'm looking at the number of tropical storms, right? So 22 is my sample size from group 1, 15.5 is my sample mean, population variance is 25.5, right? Other things I need from group 2, or the older time period, well, it's sample size, sample mean, and population variance. So if I wanted to define this difference as the difference between kind of group 1 and group 2, which here I kind of identified as the newer time period is group 1, older time period is group 2. That's typically always how you'll set up these differences. Take the newer time period minus the older time period. Because that's just how we say things, right? Like if you think about whether or not if storms have increased, well, if we set it up with the newer time period minus the older time period, well, now if we see positive values, that represents that it's increased. If I had like flipped it so that I took the older time period minus the newer time period, now I'm thinking about if they've increased, I'm actually looking for a negative difference because I'm going back in time. And it's just not how we do things, right? It's just not how our brain works. It's not how we talk. So always kind of set this up when you have time periods as the newer time period minus the older time period. Okay, so if I want to test for whether or not tropical storms have increased, what I'm really saying is, if I look at the newer time period, is the mean in that newer time period greater than the mean in the older time period? And I can't remember if these are the cutoff. I think it was 2011 was the cutoff year for the new time period and somewhere in the 80s for the old one. So what I'm really saying is that difference, right? Just rearranging this, is that difference greater than 0? That's what I want to test for. So that's my alternative hypothesis. I'll assume the exact opposite is true, which is that that difference is less than or equal to 0. Okay? So it's a little bit harder, I think, maybe to identify kind of if you have a right or left-tailed test, but just from the words when we're dealing with a two population example, because have they increased? Okay, well, if it's increased, then the difference would be positive. So what I want to test for is that difference greater than 0? I'll assume the opposite is true. But we still identify what type of test we have by that alternative hypothesis. So if I have a greater than sign, I have a greater than or a right-tailed test. Right? So if I'm thinking about my critical values, I know that they should always be what? For a right-tailed test, positive, right? Because once I know I'm dealing with a right-tailed test, when I'm looking for a critical value, remember that's the value that gives me alpha in the tail here. Okay. that standard normal distribution is centered around 0. So when I'm looking at the right tail, positive critical values, left tail, negative critical values. So I think alpha was 0.05. Oh, you would know that. Yeah, hold on. So we've got the no alternative. The next step is to jump the gun. What's the critical value at the 5% level, right? So an alpha of 0.05. Well, right away we said the critical values can't be negative. So we can cross out B and D here. From there, oops, I don't want to do that. I could go to my standard normal table, or I just always think it's way easier to use this last row of the student T table. I wanted 0.05 in that tail. So go down to the very last row of the student T table, which is my standard normal distribution values, 1.645, okay? So that's my critical value. At this point, now I can use my critical value. I know my rejection region is anywhere to the kind of right of it, 1.645. Excuse me. So now, if I'm using the critical value approach, where's my test statistic fall? Is it here? Is it here? I'll have to calculate it first. But I have that formula now. So once I have the formula, once again, I'm subtracting 0, because that was the value in our null alternative hypothesis. It always will be for these two population examples. I told you that, so that'll be easier. I just have to plug in my values, right? I can grab each one of these pieces of information from the problem. It's just a matter of kind of plugging and shoving. And until we work through kind of more examples, I can help you in identifying what type of problem, you use this equation versus that one. But, for today, we know this is our test statistical equation when we have two sample means and we know population variances. So this is the guy we're going to use. It's just a matter of plugging those values we were given in, okay? Now, one kind of nice thing about two population examples, remember, what's in my denominator here represents the standard deviation for the differences. So I know variances and standard deviations are always positive. So now if the assumed true difference I'm using is 0, that essentially goes away. Whatever difference I find in my sample means, that tells me the sign of my test statistic, right? Because what I'm doing, right, is actually, when I'm thinking about this distribution for the difference in sample means, when I am using 0 as that assumed true difference, that's what I'm saying my distribution is going to be centered around. So now if I ever see a sample difference that's positive, I know I'm going to have a positive test statistic. If I see sample evidence that's negative, I know I'm going to have a negative test statistic. So right away, if we look at what our sample difference was that we found, go back up here, 15.5 minus 9.7. So I'm going to have a positive test statistic, right? So I could rule out D right away. But then from there, it's just a matter of plugging everything in. Okay? So I get this test statistic of 4.9. Right? Where would that be plotted? Somewhere way out here, right? So would I be rejecting the null hypothesis? Yeah, I'm clearly in the rejection region here. So I could reject that null hypothesis, which if I go back and remind myself, sometimes it's easy to forget, was that tropical storms have either stayed the same or decreased, right? The difference has been negative or equal to 0. Okay, any questions over any of that? What if instead I wanted to use that p-value approach? Well, I've got a test statistic of 4.9. For a right-tailed test, my p-value is the area to the right of my test statistic, 4.9. Okay, so I want the area to the right. So if I go to my Z table, I can't even get to a test statistic of 4. I can go 3.9 something. But notice, the area to the left of 3.9 is approximately 1, which means the area to the right is approximately, the area to the left is 1, the area to the right would be 0, right? The area under the curve is 1. So now it's not exactly 0, it's just very, very close. So the area to the right of 3.9 is approximately 0. So the area to the right of 4.9 is going to be even closer to 0, right? So if my p-value is approximately 0, what levels can I reject at? Well, I always reject if my p-value is less than alpha. So no matter what alpha I choose here, if I have a p-value that's approximately 0, I'm going to be able to reject it at any level, right? 99.9%, right? Which, you know, in this example, if we're looking at tropical storms, like I'm rejecting that they've decreased or stayed the same. I found very significant evidence, right, that they've actually increased, okay? All right, any questions on that before we? Okay. So, I think we'll do kind of some similar stuff on Friday. We'll do some two population differences for proportions. But before that, we will do some work in Excel. So there's an Excel file that is two population HT blank. Right? I won't do anything with it today. We're actually pretty much almost done with class. I just want to mention a few things so we don't have to kind of start out with them. Right? So I've got different tabs down here. Here I've got kind of some Midwest schools. Here I've got some schools kind of from the South. Right? Now, one thing that we can do, right? If I wanted to find the mean for the South, I can just take the average of all these Southern schools' total undergraduate enrollments. Oops, nope, why is this being weird? Hold on. I think I'm bumping an extra key with my hand for some reason. All right, the average of total undergraduates. There we go, right? That's pretty easy, right? But what I can also do, if I have on another sheet, right? So I had this data separated by South and Midwest onto two different sheets, okay? If I do that, right, and I calculate the mean, and I have a known population variance, and I have a sample size for kind of these Midwest schools, if I'm on the South data sheet, I can actually go equals, then select the different sheet. Here was the sample mean for the total undergraduates from Midwest schools. Hit enter. And now notice it's pulling whatever's in M4, but from the Midwest sheet. Right? So I can cross-reference sheets here, which is kind of nice because, you know, otherwise I have to maybe use some average if functions and some other stuff, which isn't as easy. But if I have these separated out into two sheets, and then I can just reference those statistics I want from that first sheet, right? And that makes it pretty easy. I could also do, right, the sample size from over here, right? And now I've got kind of the values I needed from that Midwest data set. Once I have the sample size of my Southern schools, I'll have everything I need to build confidence intervals and do hypothesis testing for the true difference between the average undergraduate enrollment between South and Midwest schools. Okay. So we'll finish that example on Wednesday. I'll kind of work through how we do this on Friday, how we do this in Excel, and we'll then kind of start looking at differences between two sample proportions, right, from two different groups. Any other questions for me before we get out of here? We're good? Okay. All right, I'll see you guys on Friday.